I'm Brian.
I'm Ben.
And I'm Jaden, and this is Lab 11 on diffraction patterns.
The Fresnel region and the Fraunhofer region are areas where different diffraction patterns can be observed. The Fresnel region is associated with Fresnel numbers of anywhere less than 1,000, and the Fraunhofer region is associated with Fresnel numbers of less than 0.01. The Fresnel region is much closer to the aperture than the Fraunhofer region, and the Fraunhofer region is the Fourier transform of the aperture. Our experimental setup includes a laser collimated towards an aperture, and then the diffraction pattern from the aperture is focused onto a sensor. We go from the Fresnel region to the Fraunhofer region by moving the sensor. The Fraunhofer region starts around 10 centimeters for 116 micron slit.
We started the lab by examining several different single slits, and we observed that with wider slits, there is a narrower airy pattern that we observed. Then we compared this to the double slits. We noticed that there was a higher frequency pattern that fit inside the airy pattern of the single slit. When the slits got wider, it affected this low frequency, so it's just like changing the single slits. However, when we change the separation between the two slits, we change this higher frequency envelope in here, or higher frequency in here, and for example, making the slits wider apart makes there be a higher frequency oscillation inside this function.
We looked at the Fresnel behavior for 3 different apertures. Up close to the aperture, the pattern looks exactly like the aperture, but as you move further away, you start to see the airy pattern. For the square aperture, you can see the diffraction pattern on the outside, and you can also see the disappearing corners. Again, the edge diffraction is apparent here, and the corners of the shape are starting to get blurred.
For the triangle aperture.
The further you take the observation plane from the aperture, the more and more it looks like the Fourier transform.
For the circular and rectangular apertures, we fit our experimental data to theoretical functions. For the rectangular aperture, we fit the function to a sinc function. As you can see, our actual data is in blue, and our theoretical data is in green. Our actual data is about twice as much as our theoretical data should be due to excess light getting into the system. For the circular aperture, you can see that the sinc function, here shown in green, is not as good of a fit as a sombrero function, here shown as red. The peak of the sinc function is not exactly located in between the first two nulls. It's closer to the first one. The sombrero function is even closer to the first null.
The resolution for things like cameras is also determined by the airy function. The Verley criterion says that you can resolve points where the peak of the airy function aligns with the first null of another point airy function. So we derive this equation here that says we can resolve angles of this, and we get that the distance between 2 points that you can resolve is 1.22 lambda f over d.